Okay, so for today, we're going to talk about motion along a straight line. See, this is the simplest kind of motion in physics, wherein the particle or the body is moving along purely on the x-axis, if we're going to put it into a coordinate system, or the body is purely moving along the y. In that case, we have a free fall body. So, but before that, from the book of Romans 5:8, it says, "But God commended His love toward us in that while we were yet sinners, Christ died for us." So let's go back. So motion along a straight line. So in this chapter, we will concentrate on the simplest kind of motion, a body moving along a straight line. So for example, in this figure, we have a dragster moving from point 1 to point 2. Okay, so we have here the starting uh, position of the dragster, and we set that as our origin. And after 1 second, okay, the dragster is at position 1. And after 2 seconds, or after 4 seconds, I mean, the dragster is at the position 2, p sub 2. Okay, so to describe the motion of the dragster, we need to understand the physical quantities velocity and acceleration. So velocity is basically the change in position with respect to time, okay, over time. And acceleration is actually the change in velocity with respect to time. So let us take note that velocity and acceleration are vector quantities. So it means that this velocity and this acceleration can have, or should have, must have a magnitude and direction. So one very good example of acceleration is the acceleration due to gravity, which is nearly constant, negative 9.81 meters per second squared. So negative is included because the acceleration due to gravity is going downwards. So we labeled going downwards as negative, and going upwards positive, going to the right positive, going to the left negative. So according to our coordinate axis, but you can change that as long as you are consistent with your sign. Okay, so acceleration due to gravity is negative 9.81 meters per second squared. Okay, if we choose the downward direction as our negative, okay, so but the magnitude of the acceleration due to gravity is 9.81 meters per second squared. So another one is velocity. So for example, you're heading somewhere and you say to your friend, uh, I'm driving at a speed of 20 kilometers per hour. Okay, so your friend asks you, uh, yes, you're driving, but to what direction? Okay, you might say, I'm driving 20 kilometers per hour heading east. Okay, if you wish to go in Rizal or in Antipolo, hey, I'm driving 20 kilometers per hour north. So if you wish to go to somewhere north, La Union, Ilocos. So the fact that 20 kilometers per hour is the magnitude and the direction is either the north or east. So you're telling a complete information because actually magnitude or vectors is a quantity that has a magnitude and direction. So of which velocity and acceleration are vectors. So going back to our figure, we have here the dragster. So if you wish to find the change in position of the dragster from time is equals to 1 second and time is equals to 4 seconds, simply we need to subtract the value of the distance of this x sub 1 from the starting point and the distance of this second point from the starting point, of which we can see here that at position 1, that is 19 meters away from the starting point. Okay, and position 2 is actually 277 meters away from the starting point. So if you get the displacement x or delta x or the change in position, we shall subtract x sub 2 minus x sub 1, and x sub 2 minus x sub 1 is 258 meters, given that the values of x sub 2 is 277 meters and x sub 1 is 19 meters. So in this example, the example or the presentation, uh, the problem uses a coordinate system of which going to the right is positive, going to the left is negative, upward positive, and downward negative. Okay, that is basically the convention. Okay, so that is the displacement or the change in position of the dragster from point 2 to point 1. You need to subtract the two values. Okay? So, what is a displacement? Basically, displacement is a vector whose length is the shortest distance from the initial to the final position. So, in other words, you have a final position x sub 2 minus x sub 1. Okay? Delta x. So, displacement can be negative. Okay? Displacement is different from distance. Distance is how much the particle has traveled. But the displacement, okay, the displacement is actually different. You have a reference point for a displacement. Okay, just like what we did here in our example. From the start, here is our reference point, and the displacement is actually measured from point 2 to point 1, and we have computed this. Okay, so if you're going to calculate the displacement of the dragster from the starting position, for example, to the position 2, which is 277 meters away from the starting point, 277 minus 0 is equal to 277. Okay, that is the displacement of the dragster, okay, at position 2. But if the dragster, after he reached the position 2 and goes back to the starting point, the displacement is 0. Okay, because the initial position is the starting point, 0. The final position is still the starting point, 0. So 0 minus 0 is still 0. So we don't have any displacement. Okay, but the distance traveled is actually what? Twice 277 meters. Because this distance is a scalar, displacement is a vector, of which displacement is always what? Has always a reference, of which, in this example, our starting point. So I hope that is clear to you. So displacement is simply delta x is equals to x sub 2 minus x sub 1. So we have here the average velocity. What is the average velocity? Basically, average velocity is delta x divided by delta t. So in other words, the average velocity is the x component of the displacement, delta x, divided by during the time interval delta t. Okay, when we talk about delta, it always refers to change. Okay, so delta t and delta x during which the displacement occurs. Or in other words, average velocity is delta x over delta t, or equal to, as I've said a while ago, change is uh, subtraction. So x2, the final position, minus initial, divided by t2 minus t1. So this t2 is the time it takes to reach x2, and time 1 is time it reach to reach x1. Okay, so we have these two formulas, delta x, displacement, and the average velocity. Okay, some simple rules for average velocity. As you can see here from the figure, that actually proves that displacement is actually a vector. Okay, so for example, the dragster is replaced by a simple pickup truck. So from the finish line, okay, here is the here is labeled as point 1, okay, P sub 1. So P sub at point 1, the truck is actually 277 meters away from the starting point. That is at 16 seconds. Okay? But it traveled to the left, okay? And it reached position 2 at time is equals to 25 seconds. So if we're going to get the displacement, the final position, P sub 2, of which x sub 2 is 19 meters away from the starting point. So 19 meters divided by, or minus 277 meters is equal to negative 258 meters. Okay, the displacement from T1 to T2 is actually negative 258 meters, and that indicates what? That the body is moving along x. Okay? Negative x. So, ito yung negative x. Okay? So here are simple rules. Whenever x is positive and increasing, or is negative and becoming less negative, the particle is moving in the positive x direction and the average velocity is positive. So for 2, whenever x is positive and increasing, or is negative and becoming more negative, the particle is moving in the negative x direction and VAB is negative. So in this case, if we wish to get the average velocity of this truck, so average velocity is again basically defined as delta x over delta t. So delta x is, we have gotten the answer, negative 258. So negative 258 meters divided by T2 minus T1, of which T2 is 25 minus 16, that is 9 seconds. So if we divide these two, we shall get a negative answer, that's negative 29 meters per second. So this is basically the average velocity of the truck from point 1 to point 2 at time is equals to T1 to T2. Okay, so negative because the particle or the truck is moving in the left direction, of which we label that as our negative direction. Okay, so we have here another definition, of which it is the instantaneous velocity. Instantaneous velocity is different from the average velocity, wherein instantaneous velocity is the limit, okay, is the limit of the average velocity as delta t approaches 0. Or in other words, this is the definition of derivative. So it is instantaneous velocity along x is simply equal to dx over dt. So we have a different dx over dt here. We need to use what do you call this, derivatives, in order for us to solve instantaneous velocity. Okay, so let's proceed to our first example. So for example, a cheetah is crouched 20 meters to the east of an observer's vehicle. So here's our vehicle. The cheetah's position, okay, the cheetah's position, initial position is 20 meters from the vehicle. from the vehicle. So time is equals to 0. The cheetah charges an antelope. Okay, he actually chases an antelope here and begins to run along a straight line. During the first 2 seconds of the attack, the cheetah's coordinate x, okay, coordinate x, he is running along a straight line, varies with time according to the equation. X is equals to 20 plus 5.0 meters per second squared times t squared. Okay, so find the displacement, letter A. Find the displacement of the cheetah between t sub 1 and t sub 2, which is for t sub 1, 1 second, and t sub 2, 2 seconds. So, in order for us to solve that, let us try to write the given. The given is basically x is equals to 20 plus 5, if I'm not mistaken, meters per second squared, t squared. So, yan. So, find the displacement for letter A. This is for our letter A. What is the displacement? The delta x, okay, at time is equals to 1 second and 2 seconds. So our t sub 1 here is 1 second. Our t sub 2 is 2 seconds. Okay, let us realize that this x is the position of the cheetah as a function of time. So meaning at x is equals to 1, okay, it is clearly that the position of the cheetah is 20 plus 5 times 1, that is 25. So at t sub 1, okay, at t sub 1, the position of the cheetah is 25 meters away from the observer. So we have two displacement here, delta x, or one displacement is basically x2 minus x1. So we need to find x1 is equals to 20 plus, oops, I'm sorry, that is plus 5.0 meters per second squared times the time, which is 1 second squared. So obviously, that would be 25 meters. For our x sub 2, we shall be evaluating the position of the cheetah or the distance of the cheetah at time is equals to 2 seconds. So we have 20 plus 5.0 meters per second squared times 2 seconds squared. And that is basically 440. Once again, 4 times 5 is 20 plus 20, that is 40 meters. So to get the cheetah's displacement, simply we shall be using this formula. X2 is basically 40 meters minus 25 meters, and the displacement from time is equals to 1 second to 2 seconds is 15 meters. Okay, did you get? Okay, yes. So for our letter B, find the average velocity during the same interval. Okay, during the same interval, the average velocity is actually V ave is equals to delta x over delta t, of which at time interval t1 1.0 second and t2 2.0 seconds. So we have computed the delta x, of which delta x is simply 15 meters divided by delta t, 2 minus 1, and that is in terms of seconds. Okay, so 15, simply 15 meters per second. This is the average velocity of the cheetah at time interval from 1 second to 2 seconds. Okay, so here we are. So letter C, find the instantaneous velocity at time is equals to 1 second by taking delta t 0.1 second, 0.01 second, and 0.001 second. So the instantaneous velocity is defined as V ins as the limit of delta x over delta t as delta t approaches 0, or simply it is dx over dt, the derivative of x with respect to t. So we are asked to find the instantaneous velocity at an interval delta t 0.1 seconds. So at 0.1 second. So in this point, we shall be evaluating the position of the cheetah by taking t sub 1 plus delta t. Okay, so in this case, our first delta t is actually what? So let us remember that this formula is actually applied, or the instantaneous velocity is actually defined as what is the velocity of the cheetah at that very short interval. Or in other words, if you let delta t approach to 0, what is the velocity of that cheetah at this time, okay, at this very point in time. So as delta t approaches 0, we shall get a much accurate answer. So as you can see here, okay, we need to get the x of the delta t 0.1 second. So that means 20 plus 5.0 meters per second squared times t squared. So what is our t squared? At time is equals to 1 second, but we have a delta t of 0.1 second. So 1 plus 0.1. So 1.1 second squared. So computing that, 20 plus 5, 1.1 squared. So that is 26.05 meters. Okay? But we have computed but we have computed already a while ago the position of the cheetah at x is equals to 1, and that is equivalent to 25 meters. So this will be our x2. So in order to find the uh, instantaneous velocity, so we shall be using again the formula delta x over delta t, of which our delta x is 26.05 minus 25 meters divided by delta t 0. Oops, let me just erase this. Okay, so that is divided by our delta t 0.1 second. So our v instantaneous Taking delta t as 0.1 seconds is 26.05 minus 25 divided by 0.1 is 10.5 meters per second. Okay, let's see what will happen if we're going to take, again, because the problem is actually asking delta t is equal to 0.01 seconds, 0.01. So, as you can see, the delta t approaches 0. Okay, and if we let the delta t approach 0, then we will definitely get an answer that is most accurate to find the instantaneous velocity. Okay, taking delta t as, according to the problem, delta t is 0.01 second. So we need to get x sub 2 again because our x sub 1 is still 25 meters at time is equals to 1 second. So 20 plus 5 times 5.0 meters per second squared times 1 second plus delta t, that is 1.01 second squared. So 20 plus 5, 1.01 squared, that is 25.1005 meters. So our x1 is still 25. So getting the instantaneous velocity as delta t is 0.01 seconds. So we have 25.1005 meters minus 25 meters divided by our delta t is 0.01 seconds. So that is 25.1005 minus 25 divided by 0.01, that is 10.05 meters per second. Okay? But the problem is actually asking also if we take delta t as 0.0001 seconds. Let's try what will happen. So taking delta t as 0.0001 seconds. So x1 is still 25 meters. So our x2 now will become 20 plus 5.0 meters per second squared times 1 plus the delta t, 0.10001 second squared. So that is a very short interval of time of the cheetah. So its distance still given as, oh, we have a lot of zeros here. So 25.001, 1, 2, 3, 4, 5. So we have 4 zeros. Okay. So calculating that, still using our formula, V ins is equal to 25.001 meters minus 25 meters divided by our delta t, which is 0.0001 second. Okay, so that should be 0.001, 10.3 zeros, then 5 meters per second. As you can see, as delta t approaches 0, we have a value that is approaching 10 meters per second. Okay, here we have computed 10.5 as our instantaneous velocity. Okay, so but as delta t approaches 0, it approaches a value of 10. Okay, so we can conclude that if we wish to take delta t as it approaches 0, we still get an answer that is very, very much closer to 10. Okay? So, the answer is the instantaneous velocity is approximately equal to 10. Okay? So, that is our answer. Or equal to 10, rather. The letter D, derive a general expression for the instantaneous velocity. Okay, derive a general expression for the instantaneous velocity. So instantaneous velocity is V ins, again, the limit of delta x as and over delta t as delta t approaches 0, or in other words, dv or dx, I'm sorry, dx dx over dt. Okay? So we have a function of x with in terms of t, that is 20 plus 5.0 meters per second squared t squared. Okay. So the definition, the problem is actually asking us derive a general expression for the instantaneous velocity. And the general expression for the instantaneous velocity is simply the derivative of this function x with respect to time. So that is our v-ins, dx over dt. So if we wish to get the dx over dt of this function, we shall be having the derivative of constant in 0 plus, let me just drop off the units, 5 times 2 by power rule times t squared minus 1. Okay? So, we will be having 0 plus 10 times t raised to 2 minus 1 is simply 10t. So, that should be our expression now for v instantaneous velocity or the instantaneous velocity, 10t. Okay? So, what is this? What this equation tells us? So, we can actually find the cheetah's instantaneous velocity at any time t given this equation. So let's try. So the problem actually before is actually asking us what is the instantaneous velocity of the cheetah at 1 second. So we can actually what uh, compute for that. At 1 second, the instantaneous velocity is 10 times 1 second. Okay? Simply that is equal to 10 meters per second. And that is the answer that we are trying to get a while ago as delta t approaches 0. Okay? So, still we have concluded that our answer for letter C is correct, which is 10. So, can you get the instantaneous velocity of the cheetah at time is equals to 4 seconds? So, we can get V-ins is simply what? 10 meters per second times time, 4 seconds. Okay? That is basically, or meter squared, meter per second squared. V ins is equals to 40 meters per second. Okay? We have used the definition of dx over dt to get the expression of the instantaneous velocity. Okay? So, our next, so finding the velocity on an xt graph. So here, on a graph of position as a function of time for a straight line motion, we can label it as the, for y-axis, the distance traveled by the body or an object, and for our x-axis, the time it reached the certain distance. So if we're going to plot that, we're going to get here the average velocity because there is a change in x, okay? Change in x first, and we have, or change in x, delta x in the y direction, okay? Because our y-axis is the x, so we have change in x here, and we have delta t here. So from point 1 to point 2, there is an average velocity because there is, again, change in position, delta x, and change in, with respect to time, delta t. Okay? So we can get the average velocity. But the definition of instantaneous velocity is the limit of delta x over delta t as delta t approaches 0. If we wish to move one point closer and closer and closer to point P, but still closer, but they are never have the same position, then we will be getting what we call the instantaneous velocity x. So, as the average x velocity is calculated over shorter and shorter time intervals, as it says in this PowerPoint, its value V average delta x over delta t approaches the instantaneous velocity, such that if we are going to move the point 2 again, very, very, very close to point 1, so what will happen is that it turns out that we only have a single point that is tangent to the position versus time of the body. Okay? So that is the instantaneous x velocity, or the slope of our the tangent line tangent to a curve at a point. Okay? So that is our finding the x velocity on an xt graph. So if we have average velocity, we also have average and instantaneous acceleration. Okay, acceleration describes the rate of change of velocity with time. Acceleration, just like velocity, again, is a vector quantity. So the average acceleration of the particle as it moves from t1 to t2 to be a vector quantity whose x component a ave is given by the equation v2x minus v1x divided by t2 minus t1, or in other words, that is delta vx, or the change in velocity along x divided by delta t. Okay, that's very simple. So in this example, I will show you the given. Okay, so an astronaut left an orbiting spacecraft to test a new personal maneuvering unit. As she moves along a straight line, her partner on the spacecraft measures her velocity every 2 seconds. So every 2 seconds, his partner or her partner is actually measuring the velocity of this astronaut. By starting at time is equals to 1 second, find the average x acceleration at time is equals to 1 second to 3 seconds. So here is the information or the given. Sorry, I have not included that in my presentation. So average acceleration is what? Average acceleration A ave is simply v2x minus v1x divided by delta t. Okay? So at time is equals to t sub 1, we have 1 second, and t sub 2 is 3 seconds. So this table of values are already given, so we can actually find the average acceleration of the astronaut. Okay? So taking t2 as 3 seconds and taking t1 as 1 second, so we can subtract 1.2 minus 1.8. Okay, so from the given, so a ave is simply 1.2 meters per second minus 0.8, because that is the velocity of the astronaut at time is equals to 1 second. So 1.2 minus 0.8 meters per second divided by 3 seconds minus 1 second, that is simply 1.2 minus 0.8 divided by 2, because 3 minus 1 is 2, that is 0.2 meters per second squared. Okay, so for that is for letter A. How about for letter B? For letter B, the problem is asking what is the average velocity between t sub 1 5 seconds to 7 seconds. So 5 seconds to 7 seconds. So we have 5 seconds at time is equals to 5 seconds, and t sub to 7 seconds. So the average acceleration is simply v2x minus v1x. In this case, our v2 is 7 seconds. So we have 1.2 minus 1.6. 1.2 meters per second minus 1.6 meters per second divided by 7 seconds minus 5 seconds. That is basically 2 seconds. So let me just show you again the given. Here's the velocity at 7 seconds, 1.2, and 1.6 at 5 seconds. So, computing that, 1.2 minus 1.6, 7 minus 5, that is negative 0.2 meters per second squared. That is the average acceleration of the astronaut, okay, at time is equals to, between the time intervals, 5 seconds and 7 seconds. So for letter C, we shall be computing again the formula. Okay, the problem is asking for what is the average acceleration from t1 9 seconds to t2 11 seconds. So our velocity at 11 seconds is -1, and for 9 seconds negative 0.4. So our v2 is again, what is that? -1 and -4. -1.0 meters per second, and v1 is -0.4 meters per second, if I'm not mistaken. Okay? So if you wish to get the average acceleration for that, AAVE is still v2 negative 1.0 meters per second minus the negative 0.4 meters per second divided by the time interval is still, the time interval is still 2 seconds. Okay? So, -1 minus -4, -0.4 divided by 2, and that is negative 0.3 meters per second. And you can calculate for letter D, and it should give you an answer of 0.4 meters per second squared. Now, if you get a negative acceleration, that does not mean that the object is always slowing down. That is a false. Okay, that is a false. So, whenever we got a negative value of an average acceleration, it does not always indicate that the object is slowing down. Okay, so okay, so moving on, we have an instantaneous acceleration. The instantaneous acceleration is basically the limit again of the average acceleration as time interval approaches 0. In the language of calculus, well, instantaneous acceleration is equal to the instantaneous rate of change of velocity with time. Thus, instantaneous acceleration is equals to the limit of delta v over delta t as delta t approaches 0. This looks familiar for instantaneous velocity. Okay, the only change here is the delta v. Okay, a while ago in instantaneous velocity, this is delta x. Okay, so instantaneous acceleration is given by this formula. So in other words, instantaneous acceleration is a derivative of the velocity with respect to time. Okay, so suppose the x velocity of the car at any time t is given by the equation vx is equals to 60 meters per second plus 0.5 meters per second squared t cube. That is my mistake, that is t cube. Okay, if I'm not mistaken. So the velocity x of a particle of the car as a function of time moves in 60 meters per second plus, that is 0.5 meters per second squared, 0.5 meters per second squared times t cube. Okay? So, we have a car and the car is moving, okay, or has a velocity function with respect to time by this equation. Okay? So, the velocity of the car as a function of time is given by this equation. So, letter A, find the change in x velocity of the car in time between t1 and t2, of which t1 is 1 second and t2 is 3 seconds. Find the change in velocity. So the change in velocity is basically v2 minus v1. Okay? So, at time is equals to 1 second. Okay? If I'm not mistaken, at time is equals to 1 second, we can get the velocity 1. So, 60, I'm not writing the unit, plus 0.5 times 1 cube. So, that is basically 60.5 meters per second. That is the velocity of the car at time is equals to 1 second according to this function. So, at time is equals to 3 seconds, we simply substitute 3, okay, 60 plus 0.5 times 3 cube, and that is equal to 60 plus 0.5, 3 cube, Okay? That is 73.5. Ano ba ako? 73.5 meters per second. Okay. The change in V is actually V2 minus V1, of which this is our V2, my mistake. This is V2 minus V1. Okay, the final velocity minus the initial. So V2, 73.5 meters per second minus 60.5 meters per second. So that is 73.5 minus 60.5. That is 13. That is 13 meters per second. This is the change in velocity at time is equals to 1 second to 3 seconds. Okay? So, letter B, find the average x acceleration in this time interval. Okay. In this time interval, the average x acceleration is given by A ave, that is delta V over delta t, of which delta V, we have already computed for that. Okay? And delta V is actually uh, 13, okay? 13 meters per second divided by still the delta t from t1, 1 second, to t2, which is 3 seconds. So, basically, 3 seconds minus 1 second. So, in other words, 13 meters per second divided by 2 seconds. So, 13 divided by 2, that is 6.5 meters per second squared, because that is an acceleration. That is the average acceleration of the car at a given time interval from 1 second to 3 seconds. Okay. Letter C, find the instantaneous acceleration at time t sub 1, 1 second, by taking delta t to be the first 0.1 second, then 0.01, then 0.001. Now, this is pretty much the same from our previous example, of which we are asked to find the average or the instantaneous velocity a while ago. But in this case, we shall be computing for the instantaneous acceleration, of which the definition is limit of delta v divided by delta t as delta t approaches 0. Or in other words, that is dv over dt. Okay, so taking delta t natin is 0.1 second. So at time is equals to 1 second. So the problem is asking what is the instantaneous acceleration of the car at time is equals to 1 second by taking delta t as 0.1 second. So we already got uh, the v1, okay, or the velocity of the car time is equals to 1 second. So let me just uh, copy this. So this is 60.5 meters per second. So 60.5 meters per second. So our V2 is again what? From our given, we have 60 plus 0.5, 60 plus 0.5 t cube. So at time is equals to 1 second plus 0.1, that is 1.1. Okay, 60 plus 0.5 times 1.1 cube, that is the velocity of the car at 1.1 second. So 0.1, 1.1 cube. So that is 60.655 meters per second. So in order to get the instantaneous acceleration, so A ins, that is basically equal to delta V, of which our V2 is 60.6655 meters per second minus 60.5 meters per second divided by our delta t, which is 0.1 seconds. Our instantaneous acceleration is 60 minus 60.5 divided by 0.1. That is 1.655 meters per second squared. Okay? So, The problem is again asking, we're done with delta t as using delta t of 0.1 second. Now we're going to use delta t 0.01 second. Okay. So again, taking delta t as 0.01 second, because the definition of acceleration, instantaneous acceleration, is that delta t should approach 0. And the closer we get to delta t, the closer our answer for our instantaneous acceleration will be. So our v1 is still the same. v1 is, if I'm not mistaken, 60.5 from our previous example. So our v2 is now 60 plus 0.5 times time 1 second plus delta t, that is 1.01 cube. Okay? So 60 plus 0.5 is 1.01 cube. That is a great value, 60.5152. Let's stop at 4 decimals. So meters per second. So to get the instantaneous velocity, simply 60.5152 meters per second minus 60.5 meters per second divided by our delta t now is 0.01 second. So if we wish to calculate that, 60.5152 minus 60.5 divided by 0.01 second, that is 1.52 meters per second squared. Okay? And lastly, we shall be, according to the problem, taking delta t again for 0.001 second, because again, we should approach delta t to 0. Okay? So our V1 is still 60.5 meters per second. Our V2 now should be 60 plus 0.5 times 1 plus this delta t. So 1.0001 second cube. Okay? So 60 plus 0.5, 1.0001 cube. That should be 60.5000, or oops, 2 zeros only. Okay, so 2 zeros only, 5000150002. So if we're going to calculate A instantaneous, that should be, this is meters per second, so that should be 60.50015002. I've shown you all the decimals, so we can approximate the instantaneous acceleration as it approaches delta t. So our delta t is 0.0001 second. So that should be 60.5, 0.001. That should be 1.50015 meters per second squared. So we have a clue that our instant acceleration should be 1.5. Okay, so approximately, if we're going to round it off, our instantaneous acceleration is 1.5, because as we can see, as delta t approaches 0, the value of instantaneous acceleration approaches also 1.5. Okay, so letter D, derive an expression for the instantaneous x acceleration at any time and use it to find the x acceleration at time is equals to 1 second and 3 seconds. So today, we're going again to define or to derive the expression for instantaneous acceleration. So we have the given Vx 60 plus 0.5 t cubed. Okay? So remember that instantaneous acceleration, A-ins, is simply dv over dt. So in order for us to find an expression, a general expression for instantaneous acceleration, we can apply derivative on this function. So dv over dt, the derivative of 60, that is a constant, that is 0, plus 0.5 by power rule 3 times t squared. Okay? So our expression for dv over dt, or the instantaneous acceleration at any time t, is simply given by 1.5 t squared. What does this mean? So we can find the instantaneous acceleration of uh, the car at any time t using this equation. So the problem is actually asking find the instantaneous acceleration at 1.0 seconds. So simply A instantaneous is 1.5 times 1.0 second, and that is equivalent to 1.5 meters per second squared. And this should not be surprising because we have seen this a while ago. As our value of delta t approaches 0, the value of the instantaneous acceleration approaches 1.5 meters per second squared. So the problem is also asking at time is equals to 3 seconds, what is the instantaneous acceleration? A instantaneous is simply 1.5 meters per second squared, that is meters per second squared, or if I'm not mistaken, cube. That should be cube. Okay? So it doesn't matter as long as you know the units. Let's not just write the units. So 1.5 times 3 squared. Okay, this is in squared. So 1.5 times 9. So 1.5 times 9 is 13.5 meters per second squared. Okay? So basically that's it. The instantaneous acceleration, average velocity, and instantaneous velocity. Thank you so much for listening. I hope uh, you learned something. So thank you so much and God bless.